Hello everyone and welcome back. In today's video, we are going to be finishing talking about partial fraction decomposition. And specifically, we're going to be talking about partial fraction decomposition on fractions that look like this one and fractions that look like this one, where there is either a quadratic factor in the denominator or there is a repeated factor in the denominator. We will decompose these fractions using a technique that's very similar to this six-step process that we introduced 2 videos ago. The only thing that will really be different in this context as opposed to this context is that in step 2, the template that we set up will be slightly different. So for example, in this exercise, I have 1 over x squared plus 1, and I have x minus 3 in the denominator. And I acknowledge that here I have a quadratic factor that cannot be factored further. In a situation like this one, the only thing that changes is that in the template, put a linear factor over the quadratic. So to show you what I mean, I would take my complicated fraction that I'm trying to decompose, and I would set up the template on the right, one fraction for each factor of the denominator. But instead of putting just a constant, an unknown constant, in this numerator over the quadratic, what I would put up here is an unknown linear equation. Some number times x plus some other number b. Put a linear above a quadratic, and then above this linear denominator in the back, go ahead and put a constant. In general, the pattern here is that if the degree of the denominator is whatever it is, then the degree of the numerator is going to be one smaller. So if you have a quadratic down here with 2x's, you'll have a linear in the numerator with 1x. And if you have a linear factor down here with 1x, you will have a constant factor in the numerator with no x's. So in general, the pattern is that the numerator's degree is always one smaller than the denominator's degree. Once you have set up that template, the rest of the steps proceed exactly the same way. Once the template has been set up, we're going to go ahead and clear the fractions. We're going to go ahead and simplify. We're going to go ahead and set up separate equations using the coefficients of the different terms. And then we're going to solve the resulting systems for all of the unknowns and put them back into our template. All of that's the same as it was before. The only real change is the template itself. So multiplying through by the least common denominator, each fraction will get a copy of the factor that it does not have already. So this denominator has everything, so only the 1 will come down to the next line. This denominator is missing an x minus 3, so an x minus 3 will show up in the next line. And this denominator is missing an x squared plus 1, so an x squared plus 1 will show up in the next line. And now, if I simplify this expression by distributing, and I simplify over here by distributing, I can go into this equation and I can look separately at the coefficients of x squared, the coefficients of x, and the constant terms so that I can set up a system of 3 equations for the 3 unknowns a and b and c, which I am trying to find. So on the right side, my x squared terms are a plus c. And on the left side, I have no x squared terms. If I look at the terms containing only x, on the right side, my coefficients of x are b and minus 3a. And again, on the left side, I have no x's, 0 of those. And then finally, my constant terms. On the right side, my constant terms are negative 3b plus c. And on the other side of the equation, my constant terms are 1. So let's try and solve this system of 3 equations for the 3 unknowns a and b and c. Well, this equation here tells me that c and a are opposites. If I plug that equation into blue, then that tells me that 0 is the same thing as b plus 3c, which implies that b is the same thing as negative 3 copies of c. Now if I plug that into equation 3, I finally have an equation that contains just one unknown. 1 is equal to what is now negative 3 times minus 3c plus c. So that looks like 1 is equal to 10 copies of c, and that looks like c is equal to 1/10. So now that I've found the value of c, I'm very close to having found the value of a and b. If I just back substitute those, I find that b is equal to, from the blue equation, b is equal to negative 3 times 1/10. And from the yellow equation, I find that a is equal to negative c, negative 1/10. Now all I have to do is put these values back into the template that I set up, and from that I find that the decomposed version of my fraction is a equals negative 1/10 x, b is equal to negative 3/10, and c was equal to positive 1/10. So this expression here would be equivalent to what I started with, 1 over x squared plus 1 times x minus 3. Now that I have this decomposition, I would be able to integrate that fraction by instead integrating its decomposed version. Integrating, for example, negative 1/10 times x over x squared plus 1, negative 3/10 times 1 over x squared plus 1, that is what's become of this first fraction here, and then positive 1/10 times 1 over x minus 3. That's what's become of this fraction here in the back. Now each of these terms can be integrated using a slightly different technique. This one on the right-hand side is familiar to what we've seen in the previous couple of videos. This could be integrated using a u substitution. For example, u equals x minus 3, where du and dx would be equal to each other. This one on the far right, by contrast, I think could be integrated using a different u substitution. U equals x squared plus 1, because then the du would contain a copy of that x dx that I have in the numerator. And this one in the middle is kind of a special case. This one in the middle is exact match to the integral formula containing arctan. So if I used those 3 methods to integrate these 3 fractions, then what I would be left with is negative 1/2, negative 1/10 times 1/2 natural log of x squared plus 1 minus 3/10 arctan of x, and then in the back 1/10 natural log of x minus 3, and then plus c from that. Partial fraction decomposition. Exactly the same process if you have a quadratic factor in the denominator. The only thing that changes is the template. If you have a quadratic factor in the denominator, then you will have a linear factor in the numerator. Now, the other case that we were not able to handle in the video from before is this case where our denominator contained a repeated factor. For example, if you had x minus 4 squared, which was x minus 4 times x minus 4. Once again, the only real difference between a situation like that one and the situations that we've dealt with in the past is how the template is set up. In the template, you have a number of fractions equal to the exponent. On the repeated factor. Count up exponents, and I will tell you what I mean by that. Count up exponents in the denominator, and put constants in the numerator. Okay, so what do I mean by count up exponents? I'm going to start by writing down two fractions here on the right side. Two fractions because I want the number of fractions to be the same as the exponent on my repeated factor. In this denominator, my factor x minus 3 has an exponent of 2. That's the number of times it is showing up in this denominator. And so corresponding to that, I will have two fractions in my template. Now, in each of those templates, I'm going to put constants. One here, a, and the other here, b. And then the question is, what am I able to put in the denominator? And the denominator will be formed by counting up from 1 to, in this case, 2. My first fraction will have an x minus 3 to the first power, and my second fraction will have an x minus 3 to the second power. This is the template that I can set up to do a partial fraction decomposition on something like this. Once you have set up that template, the rest of the problem proceeds exactly the same way as always. The next thing that I would do is clear the fractions by multiplying by the least common denominator and simplifying. Then I would distribute, and I would create a system of two equations by looking at the coefficients on all the different terms here. On the right-hand side, my coefficient of x is a. On the left-hand side, my coefficient of x is 1. So I immediately get a equals 1 from that comparison. And if I look at the constant terms, on the right side, I have negative 3a plus b. And on the left side, I have no constants. So using that information together, that implies that b is equal to 3 units. Once I have found a equals 1 and b equals 3, all I have to do is take those two values and put them back into the template. This expression is equivalent to 1 over x minus 3 plus 3 over x minus 3 squared. The advantage of having rewritten this fraction with an x in the numerator in terms of these fractions that have constants in the numerator is that we can use u substitution to integrate expressions that look like this, even though we cannot use u substitution to integrate expressions that look like this. For example, if somebody says integrate this expression, you're going to have a hard time finding a u substitution that will work well. So instead, we can try and integrate the sort of alter ego of this fraction which is 1 over x minus 3 plus 3 over x minus 3 squared. If I use the substitution that u is equal to x minus 3, so that du and dx are exactly the same, this becomes the integral of 1 over u plus 3 times u to the minus 2 du, whose integral is natural log of u minus 3 u to the power minus 1. And so putting back the original u into this expression, I get this for the indefinite integral of this fraction, x over x minus 3 quantity squared. Now, if you are in a situation where you have a repeated factor in the denominator with an exponent that's different, for example, if you had an exponent of 4, then what would the template for something like that look like? If you had an exponent of, say, 4, then on the right side you would have 4 fractions, all of them with constants in the numerator. And then in the denominator, you're going to count up exponents. So the first fraction will have an x minus 3 to the first power. The second fraction will have an x minus 3 to the second power. The next one will have an x minus 3 to the third power. And the last one will have an x minus 3 to the fourth power.